In this first lecture on basic logic, I'll be presenting some basic ideas and tools that are roughly consistent with Chapter 1 of Professor Paul Teller's book, A Modern Logic Primer. Now, I say that these topics are roughly consistent because Teller and I will be discussing the same logic, but we'll be explaining it in different ways. I'll generally be covering the same thing as Teller, but sometimes one of us will say more than the other, and you'll be responsible for knowing both. Other times, I'll go beyond the text and maybe use alternate terminology or symbolism, and you'll be responsible for knowing that too. This variety is for two reasons. I think some terminology is clearer for philosophical reasons, and having things explained in different ways can be beneficial. Indeed, depending on the individual audience members, Teller's way of explaining the material may be clearer than my way of explaining the same thing, and vice versa. Therefore, each of these lectures is going to presuppose that you've read the chapter in advance, so you must read the corresponding chapters. For the purposes of this class, logic is the science that evaluates arguments. Arguments are not fights in logic. In the sciences, philosophy, arguments are about finding truth. They're not debates either. Debates are about appearing right. But arguments in logic and philosophy, they're about truth. So, the person that is the actual winner in a logical or philosophical argument is the person that walks away learning something. The person who, in a debate, would appear to be the loser. An argument is a conclusion supported by premises. Your conclusion is your belief or your claim, and premises are your evidence or reasons for believing that claim. There's no room for, oh, that's just my opinion in logic or philosophy. You must have reasons that logically support your beliefs. In other words, premises that support your conclusions. In this basic logic course, we'll be looking at two types of logical reasoning, deductive and inductive. A deductive argument is one such that, given the premises are true, the conclusion must be true. An inductive argument is one such that, given the premises are true, the conclusion is probably true. For example, consider these arguments. Argument 1. If Adam is an unmarried man, then Adam is a bachelor. Adam is an unmarried man. Therefore, Adam is a bachelor. Argument 2. If I bet on black long enough, then I will win eventually. I am only betting on black. Therefore, I will win eventually. Consider the first argument. You verify that Adam is both unmarried and a man using his historical, personal, legal, and medical records. Then you verify the definition of a bachelor in the dictionary. Notice that from the form of this argument, it's impossible that this conclusion is false, so long as all of that information is verified and true. The form of this argument makes it valid, and with the addition of true premises, it is sound. Now, consider the second argument. Is it possible that black won't come up at all? Yes, it is. Is it likely that black will not come up at all? No, it's not. What matters is that it is not certain, as in the first argument, which is true by definition. Other factors can be considered also. Do I have enough money to bet enough times for black to come up? If I have enough money for, say, 10 bets, it is less likely than if I have enough money for 100 bets. The addition or subtraction of this kind of information can make the argument stronger or weaker. But since it is not certain, as it is in the first case, it is not a deductive argument. It cannot be valid or sound. It can be weak or strong, with true premises, but it can't be valid. Inductive arguments and reasoning will be covered in more detail in the informal logic section of this course when we turn our attention to writing. Propositional logic symbolizes atomic statements, also called statement letters, which are written with the capital letters P, Q, R, and so on down the alphabet. We can use connectives, or logical operators, to build compound statements out of atomic statements. In this section, we'll introduce the logical operators not, which is denoted by a tilde, and, which is denoted by an ampersand, and or, the disjunction, denoted by a lowercase v. Consider these two atomic statements. You can have whiskey, P. You can have beer, Q. Logical operators are so called because they operate on the truth value of compound statements. Our text calls them connectives, but not all operators connect propositions. If we apply the first logical operator, the negation, we can reverse the truth values of these statements. So, the first statement would be, you cannot have whiskey, not P. You cannot have beer, not Q. We can also connect them as a conjunction. You can have whiskey and you can have beer, P and Q. Another way we can connect them is with the disjunction. You can have whiskey or you can have beer, P or Q. An important note, we use the inclusive or in propositional logic. So, when I say you can have whiskey or you can have beer, you can choose one, you can choose the other, or you can have both. Try translating the following sentences into pure logic. You can have whiskey and beer. You cannot have whiskey and you cannot have beer. You cannot have whiskey, but you can have beer. You can have whiskey or you can't have beer. How did that go? Truth tables are an algorithmic tool that logicians use to clarify every possible combination of truth and falsity of atomic statements, compound statements, and to test arguments for validity. Just as a single atomic statement can only be true or false, so can a negated atomic statement only be true or false, and the truth table would look like this. When constructing a truth table, the rows in the first column will be half true and half false, with the true half on top. This will make more sense as we go on. The negation reverses the truth value of the atomic statement. So, if P is true, the statement not P will be false. Since a conjunction has two atomic statements, there will be more possible cases of truth and falsity, as we can see from this truth table. Notice that a conjunction is only a true statement when both atomic statements are true. This will be important for you to remember. This makes sense because when I say P and Q, logically, I'm saying P is true and Q is true. Since a disjunction has two atomic statements, each column of the truth table will have the same number of cases as the conjunction. Notice that a disjunction is always true, except when both atomic statements are false. This will also be important to remember. This makes sense because we're using the inclusive or. All logical operators are truth functional. That means, depending on the truth value of the conjuncts, disjuncts, or whatever, the various operators will produce truth value dependent outputs. For example, if the atomic statement P is true in a conjunction but Q is false, then the compound statement will be false. Conversely, if the atomic statement P is true in a disjunction but Q is false, then the compound statement will still be true. Just reference the truth tables until these functions are committed to memory. Logical operators can also operate on compound statements. If we run with our previous examples, you can have whiskey and you can have beer, you can have whiskey or you can have beer, and so on. Additional logical operators can be used to express a greater variety of propositions. For example, if we negate the entire compound statement P and Q, it will read, "You cannot have both whiskey and beer," and it would be symbolized not P and Q, with parentheses. If we negate the entire compound statement P or Q, it will read, "You can have neither whiskey nor beer," and it would be symbolized not P or Q, also with parentheses. A quick note on the nature of the negation. The negation symbol only negates the nearest whole statement to its right. Here are some examples. Not P. P, whatever it means, is a whole statement. Not P and Q. P and Q is encased in parentheses to communicate that the whole conjunction is being negated, not just P or Q are being negated. If we introduce more propositions, we can further compound compound statements using logical operators and different styles of parentheses. Let's add the statements, "You can have steak," R, and "You can have potatoes," S. We can connect or operate on these premises in different ways with our logical operators. For example, the compound statement, "You can have whiskey or beer, but you can have steak and you can have potatoes," would be symbolized as P or Q and R and S, with parentheses around both compound conjuncts. Notice that but has the same meaning in logic as and. In English, we sometimes add meaning to words out of custom that the word itself doesn't strictly communicate. But is often associated with a reason not to do something, but that's not the word's fault. Or I could say, and that's not the word's fault. See what I mean? This is part of the ambiguous nature of ordinary language that logic seeks to remedy. If we need to add more statements or operators, we'll need to use brackets to preserve the exact meaning of the statement. For example, we can negate the whole statement as not P or Q and R and S, and we can see that the whole statement has been negated using the outer limit brackets. Teller gives us some helpful formation rules, and these would be good to remember as we work through Teller's text. The rules of valuation that Teller provides are also helpful. They're essentially what I've already explained, but he puts them in a really concise form here. And that's it for Chapter 1. This isn't easy for everyone, so I recommend rereading the chapter and trying a few of the problems from the exercise sets. This will help with the homework and quizzes. Next time, we'll be looking at transcriptions versus translations.